Hey, AP Statistics. So welcome to the second part of section 9.2, where we're going to be doing our one sample z-test for p. We finally put our name on it there. We'll also call this a one proportion z-test because that's how it shows up in the calculator. But we've got that same four-step process. Same, but some minor changes. So we've got our state, our plan, our do, and our conclude. Now the state actually is one of the things that changes a little bit. So we want to state the hypotheses you want to test and the significance level and define any parameter you use. So there's a little more to it. Before we just said we're going to choose where we stated the confidence level and define the parameter. Now we want to state the hypotheses as well. And so we know our null hypothesis, H naught is this, HA is that. And so we're going to do that. Then plan is pretty much the same. Identify the appropriate inference method and check conditions. So for now, in this chapter, we're going to be doing one sample z tests for p, and that's going to be the name for all of the section 9.2 stuff. But eventually we're going to have the one sample t test for mu. And then, of course, you can mix in the confidence intervals from last chapter, and we start to have, be up to 4 methods by the end of this. So identify it and check the conditions. Then we do it. And so if the conditions are met, perform calculations. So you should give the sample statistic, or statistics in the future, don't worry about that for now. Calculate the standardized test statistic, so that's basically for now the z-score, and find the p-value. So you need to do all 3 of those things. And then draw your conclusion. Make a conclusion about the hypotheses in the context of the problem. Because p is less than alpha, we reject the null and accept the alternative that, and put context in there. All right, so there are 3 conditions that must be met for the formula for the standardized test statistic to be valid, one for each of the 3 components of the formula. So this has kind of been true of all of the confidence intervals as well, but just to hit it again. So p hat, that value that we're going to use, we need to know that it is unbiased. And so that's where the random condition comes in. Is that a good estimate of the sample proportion? And so it helps ensure that p hat minus p naught is a good estimate of the difference between the true value of p and the null value of p naught. So is it estimating the actual population proportion, p, which is why we call this p naught, by the way, because it's not necessarily p. We're assuming it's p. For the purpose of doing the problem. The second condition is that they're writing in here is z. I don't always do that one second. I usually do that one third. But that's basically that we're doing a normal distribution, and that's our large counts condition. N times p and n times 1 minus p need to be at least 10. So that shape of that sampling distribution is approximately normal. So that's one, and then the last one is that standard deviation formula requires independence, which requires the 10% condition. So this allows us to use the familiar formula for the standard deviation of the sampling distribution of p hat, with p naught replacing p when we are sampling without replacement from a finite population. All right, so we will perform our tests. So supposing the conditions are met, perform the test of p equals 0, computer standardized test statistic. We'll take our sample proportion minus the null hypothesis, divide all that. Find the p-value by calculating the probability of getting a z statistic this large or larger in the direction specified by the alternative hypothesis, HA, using the standard normal distribution. So we've done a bunch where it was less than, like this, where we said, oh, the alternative hypothesis is that the actual proportion is less than p naught, whatever our null hypothesis value is. But we could go greater than. We could do this one tail. These, remember, are 2 one-tail tests if it's greater than or less than. But 2 tail is a bit weirder, and we haven't dealt with that yet. So you take whatever your z is, and then you go above the positive version of it and go below the negative version of it. And you actually add those 2 areas together. And ultimately you're saying, what's the probability I would get something this far away? So we want to make sure that whatever our significance level is that we set, that we're looking for something to be less likely than that. And if we don't know which way it's going, we want to find what's the probability I would get to something that far away in any sample. And so we don't want ultimately to add up 5% on this side plus 5% on that side when we're looking for an overall 5%. We want to split that. And so we calculate our p-value a little differently for our 2 tail tests. We have to add up those 2 areas. So, recall the potato chip problem. The potato chip producer we met in section 9.1 and its main supplier agree that each shipment of potatoes must meet certain quality standards. If the producer finds convincing evidence that more than 8% of the potatoes in the shipment have blemishes, the truckload will be sent away to get another load of potatoes from the supplier. Otherwise, the entire truckload will be used to make potato chips. The potato chip producer has just received a truckload of potatoes from supplier. A supervisor selects the random sample of 500 potatoes from the truck. An inspection reveals that 47 of the potatoes have blemishes. Is there convincing evidence at the alpha level 0.1? So we're apparently, that's a pretty high alpha level. I mean, it's not absurdly high, but it's a higher one. So we're kind of okay with the type 1 error, which we could address more later, but it is that, there are actually 8% blemished, but we reject it and send it back. So that would be, we're okay with that. Is there convincing evidence at the 10% level that the 0.1 alpha level that more than 8% of the potatoes have blemishes? All right, so we are going to do basically the full on state plan do conclude. So state. We want to state our, hypotheses and our significance level and define our parameters. So in this case, our null hypothesis is that P is 0.08. Our alternative is that it's more than 0.08. And then where P is the true proportion of potatoes in this shipment with blemishes, and we're using an alpha level of 0.1. So you can write that in another order, but that is our state step. There's a little more to it now. The conditions, these are in the plan, the name and conditions are pretty similar. So plan, we're going to do a one sample Z test for P, one sample Z test for P, or you could say one proportion Z test. And then our conditions are 3 conditions, random, they got a random sample of 500 potatoes. We're going to assume that that's less than 10% of all potatoes in the shipment, and they say it's reasonable to assume, so you could just say we will or whatever. So it means there need to be at least 5,000 potatoes in the shipment. And then the large counts, N times P naught, so P naught was 0.8, so 500 times 0.8. Is 40, which is at least 10, and 500 times 1 minus that, so 0.92 is well over 10. And so we've made our conditions for normality and independence and unbiased. So then finally we get to do actually calculate the values. So we use our sample proportion, 47 out of 500, which is 0.094. So 9% of them are blemished. Is that enough to make us reject the whole batch? So we find out 0.094 minus 0.08, and then we divide by, and then we use that null hypothesis for our standard deviation, because we're doing the whole problem assuming that there really are 80%. What's the probability I would get this? 9.4 when it really is 8% for the entire load. So we calculate that Z-score. With a z-score of 1.15 or 1.15 standard deviations above the mean. You could use your z-table or probability technology more likely, normal CDF from 1.15 to infinity. With that mean of standard deviation, we get a p-value of 0.1251. So that's our p-value. It's bigger than alpha, so we don't find significant evidence. Because our p-value of 0.1251 is greater than alpha, we fail to reject the null hypothesis. There is not convincing evidence that the true proportion of blemished potatoes in the shipment is greater than 0.08. So, did not quite find significant evidence. We got a lot of blemishes, but it could just be sampling variability. That we get something like that 12% of the time. It wasn't quite below that threshold we were looking for to reject. AP exam tip: when a significance test leads to a fail to reject the null hypothesis decision, as in the preceding example, be sure you interpret those results as we don't have convincing evidence for the alternative. Saying anything sounding like you might believe the null hypothesis is or might be true will lead to a loss of credit. So you don't say, we'll believe that this shipment is good. We'll just say we failed to find evidence that it was bad, or failed to find evidence that more than 8% were blemished. So make sure you do something like that. So it would be wrong to conclude there is convincing evidence that the true proportion of blemished potatoes is 0.8. We never accept the null hypothesis or prove it true or something like that. And then don't write out words. You write out that sentence. Don't write FTR the HO like a text message. What does that even mean? Don't make your reader try and decode that, because it might be bad. I think they're trying to say fail to reject the null hypothesis. So don't write that. Another AP exam tip, you can use your calculator to carry out the mechanics of the significance tests on the AP statistics exam, but there is risk involved, so you don't actually have to write out the formula. I'm going to make you do it for this chapter, just like I did last chapter, but eventually you don't really have to. You can just do the one proportion z-test in your calculator. However, there is risk with that. If you give just your calculator answer with no work, and one or more of your values are incorrect, you will probably get no credit for the do step. If you opt for the calculator-only method, be sure to name the procedure, a one-sample z-test for the proportion, and to report the standardized test statistic, z, and the p-value. But it's harder to get partial credit when you don't really show any work. If you showed work and you actually just screw up a single little number, you might still actually get full credit even, because they can overlook some little silly errors and still give full credit for those problems. All right, so finally, let's just do a two-sided test. The p-value in a one-sided test about a proportion is the area in one tail of the standard normal distribution, the tail specified by the alternative hypothesis. So if it's greater than, we go to the right. If it's less than, we go to the left. In a two-sided test, the alternative hypothesis has the form p is not equal to p0. The p-value in such a test is the probability of getting a sample proportion as far or further from p0 in either direction of than the observed value of p hat. So wherever our p hat ends up, if it ends up over here, we find that area plus the area in the other direction. And so we're looking for significant evidence against p in either direction. And so that's how we calculate our p-value. So, one more example with this, full-on state plan to conclude. According to the Centers for Disease Control and Prevention, CDC website, 68% of high school students have never smoked a cigarette. Yan Hong wonders whether this national result holds true for her large urban high school. For her AP Statistics class project, Yan Hong surveys a simple random sample of 150 students from her school. She gets responses from all 150 students. Wow. Great, no non-response there. And 90 say that they have never smoked a cigarette. Let's hope that there's no response bias there. It is convincing evidence. Is this convincing evidence that the CDC's claim does not hold true at Yan Hong's school? So we're going to perform the test to see if it's ultimately, is there convincing evidence that the CDC's claim does not hold true? She's not saying more or less. We're not trying to see if it's one way or the other. We're just doing not equal to. So our null hypothesis is 68%. Our alternative is not equal to 68%, where p is the proportion of students in Yan Hong's school who would say that they never smoked a cigarette. And we're going to use an alpha level of 0.05. And interesting that we say said, because that kind of covers our potential response bias of people who don't tell the truth. Let's see, did this one suggest, sometimes the problem will suggest an alpha level. If not, you can pretty much just use 5%, or any reasonable one you can technically get away with, but I would recommend 5%. So they did not state it there, so we'll go with the 5% alpha level. So we've done all our parts of our state. We've stated the hypotheses, defined the parameter, and stated our alpha level. And so then we move on and call this a one sample z-test for p. We've got our random condition, got a random sample of 150 students. We'll assume that's less than 10% of the population. And then the large counts condition, we're going to check n times p naught, which was 68%. That's the assumed proportion. And n times 1 minus that. And both of those are at least 10. So we're good to go ahead and do this. So we find our sample proportion. This is our test statistic. 60% is what was actually observed, which is not the same as 68, but is it far enough away? So we do 60 minus 68, and we get, and divide by the standard deviation with the square root of 0.68 times 1 minus 0.68 over n, and get a z-score of negative 2.1. So then when we go to do this, calculating our p-value, that's our standardized test statistic, we need to go below negative 2.1 and above positive 2.1. And those two areas together add to be our p-value. So you can do a couple of different normal CDFs, or you can just do 2 times a single normal CDF. So this is what they're doing here. Basically, they went from negative infinity up to negative 2.1 with mean 0, standard deviation 1, and then just did times 2, because this is going to be the same because it's symmetric. You could also have gone from 2.1 to infinity and with the same mean and standard deviation and doubled it. And so we get a p-value of 0.0357. And so we have done our work. And so now we're ready to conclude, and we get to compare that to alpha and draw our conclusion. So they do this in the kind of the 2 sentences. Because our p-value of 0.0357 is less than alpha, we reject the null hypothesis. First sentence is kind of simple. Make sure we always address that. And then to address the alternative as well. We have convincing evidence that the proportion of all students at Yanhong School who would say they have never smoked a cigarette differs from the CDC's claim of 0.68. We just conclude the alternative. We don't say it's more than or less than. We don't go back and look at our data and draw a conclusion based on a particular direction. We just say it's different from that. We could follow that up with a confidence interval for what it is, and that's oftentimes what people do. But the only conclusion we should draw is based on that alternative hypothesis. We should either, accept, or the alternative hypothesis there was accept the alternative hypothesis that it's different 0.68, or fail to reject, fail to accept, find insignificant evidence of anything. So in this case, we did find a small enough p-value that we could reject that null hypothesis and accept that it's different. AP exam tip, last one. When making a conclusion in a significance test, be sure that you are describing the parameter and not the statistics. So make sure the proportion of all and things like that. In the preceding example, it is wrong to say that we have convincing evidence that the proportion of students in Yanhong School who said, and this is a really easy one to miss, who said, we have to say would say, because said refers to the sample specifically that was already questioned. So don't use that word. Said they have never smoked differs from the CDC's claim of 0.68. The proportion who said they have never smoked is the sample proportion, which is known to be 60%. The test gives convincing evidence that the proportion of all students at Yanhong School who would say they have never smoked a cigarette differs from 0.68.